Hopefully it goes okay. Let's go. So what the goal of today is, for me at least, is to report on some work in progress that I've been doing. Initially, this project was started in Poisson 2018, and the goal-ish was to have it finished by Poisson 2020. Well, as you see, it's still work in progress, so we didn't make it. And I started working on the project with Sunghao Lee, who you might know. So part of it is joined with him, but he has recently left mathematics, so I'm doing it on my own now. The goal of the project is to, well, first of all, describe the geometry of certain class of Poisson manifolds, which are called elliptic, and then more so construct their associated groupoids. And the ones we're focusing on are the so-called adjoint groupoids, which, if you know what that means, they are the smallest ones. And there will be a few of them around, but in particular, we want to know what adjoint symplectic groupoid integrated into Poisson structures. So we're going to go into the outline real quick, and we need to first describe a little bit about just general stuff about elliptic Poisson manifolds, part of which is also new. And then we move on to the groupoid stuff. First, some generalities. You see my cat in the back. And then for the elliptic ones in specific. Okay, so let's go. The elliptic Poisson manifolds are defined by having certain types of singularities. So how we capture what these singularities are is by using the notion of a divisor, which may be familiar to you. I see that there are actually quite a few people here, so I don't know what everybody's background is, but I'm going to assume a little bit, for example, that you know how log symplectic manifolds work. Anyways, the divisor is just a line bundle with a section, and the section captures how degenerate something is, basically by which ideal it induces. I don't know if you can actually see my cursor, but there's a divisor ideal here. This is the thing that's measuring like how singular something is. We basically today only deal with two of these. The simplest of which is the log divisor one, which I hope you're familiar with. It's just where the section sigma has transverse zeros. That means its zero set will be a hypersurface, so codimension 1. And locally, this thing is just the vanishing function for that hypersurface, which is like z or something, or x, whatever you want. The elliptic ones are a little bit more complicated. There you have like second order vanishing, and the sort of intrinsic definition is that there's some normal Hessian which is definite. It's basically locally given by the zero set of a definite Morse spot function, and you can write it like this. So it's locally r squared, where r is radial coordinate in the normal bundle to d. Okay, cool. Now, how to bring Poisson geometry into the picture is by noting that if you have an even dimensional guy, then you can just take the top wedge of the tangent bundle and the top exterior wedge of pi, and then you get a pair as in the previous definition. So there's also an ideal like this. Typically, such a pair is not a divisor, of course, because for that you need it to have nowhere dense zeros. But we can define classes which satisfy this. They get the log Poisson condition by demanding it's a log divisor, and the elliptic Poisson if it's an elliptic divisor. Okay. Now, the first of these might be familiar to you under different names. They're also called B Poisson or log symplectic or B symplectic. The reason I call it like this is because it's more consistent in my opinion with the other ones. And it's just saying like it's a Poisson structure with a certain type of degeneracy. Namely, its divisor is of log type. The second ones have also already appeared in the literature. They started with the work of Cavalcanti-Galtieri on stable Giants complex structures. As you might know, a Giants complex structure always has an underlying Poisson bivector. And as it turns out, for stable ones, these are elliptic. But what we care about today is not so much this stable GCS stuff, but really just the Poisson geometry of the guy itself, not necessarily whether it's coming from a Giants complex or anything.
Ralph, let me ask you something.
Yeah.
In algebraic geometry, you can also define divisors by looking at hypersurfaces, no?
Yeah.
And how is this related? Does this zero section, the zeros of a section determine completely the line bundle in this case or not? Or is it?
Yeah, so just going to go back to the definition. Thank you for your question. I interpreted it as saying that you can also just look at the hypersurface instead of this more complicated, possibly line bundle with a section. In this case, in the log case, it's true that, as you know, as you can see here, the ideal is just the vanishing ideal of the hypersurface. So basically all the information is just the hypersurface. However, for the elliptic ones, because it's codimension 2, and you can have more complicated examples where you take products and all sorts of things can happen, it's not necessarily true that just the 0 set determines everything. So you can have several same submanifolds D with different elliptic divisor structures on them. So it's really a little bit more information than just the 0 set. But of course, the ideas are very similar. That's also why we call it a divisor in the first place, right? It's basically the concept from algebraic geometry, except because we're working with smooth stuff, yeah, we need to keep track of this. One other thing to note is that basically the only thing you need to remember is the ideal that determines it up to isomorphism. But we keep track of this line bundle on the section because that's sort of how you encounter them via this Poisson thingy over here and also for the algebras later. Okay.
Yes.
Yeah.
Sorry. Another question. In the definition of elliptic divisor, the condition that the vanishing is along a codimension 2 is is it a condition or it's a consequence? It's a hypothesis, right?
No, you need to put it there. Yeah, it's like what is the definition of a Moore spot function?
Correct.
It's basically like that. Like here's the line bundle in the section, but of course you can always locally trivialize the line bundle, and then the section just becomes a function. And then this condition is just saying that it's a Moore spot function in a certain sense. Okay, moving on. So what we're going to do now is study these elliptic Poisson guys. And the first thing you note, of course, is that because you look at the top wedge of pi, it's only 0 on D. It's not 0 anywhere else. So the pi vector is non-degenerate everywhere else. And yeah, the D is the degeneracy locus. It's Poisson submanifold, so that it has an induced Poisson structure. What we want to know now is what is the behavior of pi near or on D? And for that, we make use of a tool that's familiar from log geometry, of course, and that is the use of Lie algebroids. So in the elliptic case, you basically make exactly the same definition as you do there. Namely, you look at all vector fields on X, which preserve the ideal that you get. So preserving the log ideal is just equivalent, because it's a closed thing, to being tangent to the submanifold. However, here it's a little bit more. So if you would use these coordinates r and theta from before, then the elliptic tangent bundle you get in this manner is locally generated like this. So it's these specific two vector fields that you use, which are normal to D. It's not just, so this will be x ddx plus y dy, and this is y dx minus x dy. It's not just all 4 possible linear combinations, because that will not give you a projective module. So you need to use these specific ones, and then by Serre-Swan, you get a Lie algebroid. So this was already known by Cavalcanti-Artieri, of course. So what you can then do is, using this Lie algebroid, define something called a lift. So basically, you write down the definition of a Poisson structure, but now using Lie algebroid objects. That's what I've written here. And then as it turns out, you can lift pi to this guy. So you find another one, pi prime, which is now in the elliptic tangent bundle. And yeah, it sort of projects down to pi using the anchor map O. The reason why you'd want to do this is because now, while pi had degeneracy, as we saw, this guy pi prime does not. So the Lie algebroid version of it does not have degeneracy anymore. And in fact, then it becomes dual to an elliptic symplectic form. This is also true in the log case if you replace elliptic by log everywhere. So the goal now is to study pi using this elliptic symplectic form omega. Now, how do you go about studying them? Well, you need to use information of the specifics of the Lie algebroid in some way. And basically, the way in which you can plot different forms in the Lie algebroid is by using residue maps. So here's a sort of nasty slide explaining residue maps in this case. What we need to write it down in this manner is a co-orientation of the submanifold D. And then, yeah, there's a bunch of maps I'm writing down here, but maybe your attention should be focusing on this omega over here. If you just look at the local description of the Lie algebroid, any local elliptic 2 form, or form in general, can be written in this manner. So you have the singular generator d log r, the singular generator d theta, and then their wedges. And then what the residue does is sort of take coefficients in front of some singular generators when it makes sense. So the elliptic residue that I'm writing over here is asking what is this alpha, and the radial residue is asking what is in front of d log r, and the theta residue is asking what is in front of d theta. You might wonder, okay, there's also this part over here, yeah, But that's why I'm writing that I only look at the theta residue on the space of forms which have 0 elliptic residue. So first we demand that alpha is 0, and then we ask, what is this? So this is a general fact you can do with these types of Lie algebroids. They are all generically isomorphic to the tangent bundle, except on some subset. And then the residue maps sort of ask you what are the coefficients in front of the singular generators that you get there. Okay, so this is the residue. So now let's do it. So let's apply the residue maps to our symplectic form.
Sorry to interrupt again.
Yeah, of course.
In the previous slide, you said something about conditions that you're imposing. You don't want alpha, for instance, to be 0, right?
No, what I'm saying is that it makes sense invariantly to ask, quote unquote, what is the coefficient in front of d log r? That is applying the radial residue map. And then what it turns out is you get something in this. So this is the S1 bundle of the normal bundle, and then the Tia algebroid of that. That is a Lie algebroid over D. And you get a Lie algebroid form in there. So that is some object. However, it is not so clear to describe what asking just what is the coefficient in front of d theta would be, because you would get both gamma and d log r wedge alpha. And that as a combination is not a nice object. So instead, I only define this theta residue in the first place on forms in which I already know that the alpha coefficient is 0.
Oh, okay.
Then this guy doesn't exist, and then it's just this. So that's why you only get the pullback of gamma over here.
Thank you.
Yeah. So yeah, this takes a little bit of time to digest. I realize that. The main one we're going to focus on now is the elliptic residue. That's taking away sort of both of these singular generators. And if we apply it to omega, we get a 0 form. And because something I didn't tell you yet is that these residue maps are all cochain morphisms. Because omega is a symplectic form, it's closed. So also residues of it will be closed. So lambda is a closed 0 form. That means it's a locally constant object. And we can sort of make a dichotomy for the elliptic Poisson guys, depending on whether it's 0 or non-zero. Of course, if D has multiple connected components, it can be 0 over here, non-zero over there, but that's sort of irrelevant. Like let's focus our attention on when D is connected, and otherwise these regions don't really talk to each other, so that doesn't really matter. If you know the background coming from the Cavalcanti-Gautieri paper, the case where lambda is equal to 0 is the case corresponding to stable generalized complex geometry. And the non-zero case is there, for example, not treated. Okay, so what can we do now? Yeah.
Let me interrupt again. Since the zeros of the singular locus is nowhere dense, yeah. I guess that the anchor map is somehow injective, no? Or insection.
Yeah, it's what you say. It's called almost injective. That is saying that it's injective on the level of sections, or it's injective in an open dense sets. That's true, yes. So
can we think of it as a...
Sorry?
No, please, go on.
These Poisson structures that we're dealing with here, they're almost everywhere non-degenerate. So also the Lie algebroids that we use to desingularize them are almost everywhere isomorphic to the tangent bundle, except on the locus where the interesting stuff happens.
Okay, so I want to ask, so can I see through the anchor map as a singular foliation, this Poisson structure?
Yeah, that is something we'll be doing later on, because there'll be, for example, this Lie algebroid, the elliptic tangent bundle. We want to find, for example, its integrating groupoid, and we do that in a manner which you're alluding to, I think.
I see. And my last question related to it is if these residues that you defined for us can be related or can be thought of as the bound-bot residues for singular foliations. Are they related?
Possibly. That I would not be able to answer straight away, because I'm not too familiar with the concept you're describing. So I don't know, maybe. Okay. So the first thing you can do is apply the big residue, the elliptic one, to omega, just straight away. Then you get this dichotomy. So the next thing you do is to realize that this is already enough to find out pointwise Darboux models for the structure. So there's a little bit of a story here. Namely, for these types of Lie algebroids, you have Moser methods at your disposal. It just basically copy the proof line for line. There you go. And then, of course, in the Darboux theorem there, you're using at some point some cohomological conditions. So you need to know what the local cohomology is, the Lie algebroid in this case. That is, in fact, governed by this residue that we're taking. And then there you go, you get this. So these are the two Darboux models that you get. Yeah, you see that the behavior of the Poisson structure depends on the residue, because the induced Poisson structure on D has, if X is dimension 2n, has either rank 2n minus 4, so it drops by 4, or it drops by 2. Yeah. Okay. So the next thing you can wonder is a little bit more globally what's going on, not just the pointwise Darboux. And there, the first thing to notice is that we have this elliptic symplectic form omega, which of course then orients the Lie algebroid in which it lies. But because the Lie algebroid is basically the tangent bundle except on a codimension 2 subset, that means their Stephen-Whitney classes are the same. So the X is also oriented because Tx is. It inherits an orientation from omega. That is unlike the log Poisson case where this is not true. The other thing then you can do is to try to get a little bit more information out of omega. And then it's a useful thing to realize that, yes, omega is basically all the structure that there is. It fully determines pi. But it's a little bit more convenient here to think of omega not so much as a 2-form, but as the full spinor line. So the pure spinor line it generates. So in a way, more think of it as its Dirac structure. Now, this is some line of forms, right? This is like 1 plus omega plus 1/2 omega squared. And you can just apply the residue map term by term to all of them. It's a linear operation. So if you do that, I'm writing here some stuff. I need to make haste a little bit. So for some of these things, I'll just ask you to read as I'm saying things. If you apply the elliptic residue to the full e to the omega, you see that locally it can be expressed in this manner, where alpha 1 and alpha 2 are closed 1 forms, which you can also obtain via the, oh, there should be a theta here instead of a q. The residue maps applied to omega directly. And if you then look at what the top degree one gives you is this is non-zero. So this beta is pointwise inverse to the Poisson structure on D. And you see that it's regular of corank 2. And the alpha 1 and alpha 2 are giving you the symplectic foliation. So they're closed 2 forms. And their kernel is spanning the symplectic foliation for you. This beta guy is not globally closed. So it's only a local object to begin with, but it's not closed on D, but it is sort of leaf-wise closed, as you can see here. This is in the case where lambda is equal to 0. So this is the stable GC case, if you want. The other case is perhaps a little bit more pretty. You just define a 2-form in this way. So you take omega squared, it's a 4-form. You apply the residue to it, it's a 2-form again, and then you divide it by this possibly strange factor. The reason to do this is then you get this nice relation. So the residue of the whole spinor line is again lambda of a 2-form, e to the 2-form, and this guy is in fact symplectic. So you see now that the Poisson structure on D in the non-zero residue case is non-degenerate. Yeah, there's some yeah, it's not directly inverse to pi d because I did this rescaling. And there's, of course, some interpretation to be done with what is this lambda, and there's some volume interpretation there. What is this too? But the summary is that X is always oriented by pi. And if you have this co-orientation, you see that the induced Poisson structure is either corank 2 regular. It's in fact a little bit more because we have these 2 1-forms, alpha 1 and alpha 2 around, or it's just non-degenerate. Yeah, if there's no co-orientation, the description of even these residues is a little bit more annoying, and that sort of carries through the whole theory. So don't think that something like a co-orientation is just, oh yeah, let's put it there and then move on. This is actually changing the Poisson geometry because there's an interplay between what's happening on D and what's happening normal to D. But yeah, I have to focus my attention here, also because it's work in progress, on the co-oriented case. Otherwise, I know things are more complicated. Okay, so now we have a little bit of an idea what elliptic Poisson manifolds are. Namely, they have a certain Darboux model, and we know, in fact, what the induced structures on D is.
Can I ask something?
Yeah.
You're saying that if it's, that you have to impose this condition, but you think condition, of course, holds always locally, and the conclusions are local, right?
Yeah, that's right. Yeah, but obtaining these one forms, especially the one out of the theta residue, that sort of depends on having the co-orientation.
Okay, what is written in the almost two co-symplectic? That's what you mean. Oh.
Yeah, this is a notion that's also appearing in the thesis of Boris Osorno Torres. It's like, yeah, you can have n co-symplectic. They have a bunch n one forms, which are pointwise linearly independent, and they have a two form, and they span the foliation. The almostness is saying that we don't impose a condition of them all being closed. Here, the one forms are closed, but the two form is not closed. It's only leafwise closed. Yeah, this is something that you can ask me later, maybe. Yeah.
Thank you.
Yeah, one thing maybe also to point out that I worked with Gio Cavalcanti on some of this stable GC stuff. And there we were able to construct, for example, zero elliptic Poisson manifolds where the D is not co-orientable. So these are certainly there. They just appear, but I'm not covering them here. Okay, so one thing that you can also prove, and that's something you might want, is not just the pointwise Darboux model, but in fact the semi-global normal form. And I might have the time to discuss this a little bit. This is based on the work of Aldo Witte. So I told you before that the Lie algebras we use here, they have Moser methods at their disposal. And that doesn't really just work pointwise, it also works like semi-globally. But of course, one thing you then need is to build the models to which you want your structure to be equivalent to. And here is a sort of outline how to do that. So we again need a co-orientation. Then what we know is that if you use the elliptic ideal, this is IID, the ID together with the co-orientation specifies uniquely a compatible complex structure on the normal bundle. Of course, if you just have a co-orientation on a rank 2 vector bundle, there's a whole bunch of complex structures on it which are compatible with that orientation. But because it must also be compatible with the ideal, there's in fact a unique one. So the co-orientation supplies you with a complex structure, and then you can find a complex connection on it, which has some curvature. And this allows you to construct two global objects, which are called the rho and theta. And they are sort of the global counterparts of the local coordinates d log r and d theta. They're of course not closed as I'm writing here. They depend on their curvatures or their differentials depend on the curvature of the connection. But once you have these objects, it's sort of straightforward what to do now. Namely, replace the objects in the Darboux model by these more global counterparts, and you get this result, which I hope I'm paraphrasing correctly. So it depends, of course, again on the residue. So lambda is equal to 0, lambda is not equal to 0. If it is equal to 0, let's cover that one first. You get basically exactly the same thing that I was writing before. This is d log r, this is d theta, this was dx1, this was dx2, and you pull back the two form you have on d. Yeah, the way you obtain the two form on d is via some sort of Hartley restriction process, which I can't really get into. But there's a way to extract out of the Poisson bivector some data, build a model, and then show that that thing is an actual model. So it gives you the semi-global normal form. In the latter non-equal case, it's a little bit easier. The reason why I bring this up is that later on we will need it, but I won't really cover how I'm actually using it. But it is important that this result exists. And the second thing you can do using this result is what's on the next slide, namely, you can prove something that's similar to what happened in the log-Poisson case. Just to remind you, perhaps, in the log-Poisson case, we only have a hypersurface, right? It's called Z. And there's also a residue map there, which just asks what is the coefficient in front of d log Z. If you apply that to the log symplectic form, you get a one form, it's closed. And you can perturb the whole structure so that this one form gives you a fibration. This is like Tischler's theorem, and then you need the normal form for the Poisson structure to be able to do that globally. That then shows you that Z must fiber over S1. Now, this is the analog of that, namely the whole structure pi can be perturbed so that it is proper. So the induced structure on D becomes having compact leaves, and the one form alpha 1 and alpha 2, which are obtained via the radial and theta residue, give you this vibration at the bottom, P alpha 1, alpha 2. So let's see how I'm doing on time. When do I start? Do I have like 30 more minutes or a little bit more?
A little bit more, but yeah, you don't have to worry too much about the time. I mean, it's not. We can have 5 or 10 more minutes, or go on indefinitely if we want.
I see.
Right.
Well, so one of the things, as I said, that comes out of the normal form is this result, and this is something that we'll use. Okay. So the next thing we need is something that was noticed by Cavalcanti-Gaucheri. They didn't write it up, and after that, Kirchhoff-Lückau did write it up. At the same time, I also formulated it in my language. Basically, what you can do is take an elliptic Poisson manifold, and then, well, you have a codimension 2 submanifold. Yeah, it's D. So you can apply real blow up to it. So you get the X being the blow up of D. X tilde is the blow up of X along D. And Z is the S1 bundle of the normal bundle. That's now a manifold with boundary. As it turns out, if you do this, this is sort of compatible with the Lie algebroids that are around. So if you do the blow up, you get an induced Lie algebroid morphism from the log tangent bundle to the elliptic tangent bundle. And yeah, this is a fiberwise isomorphism. So it's not doing too crazy of a thing. And moreover, it sort of intertwines the residue maps that are around in this manner. So applying the radial residue downstairs and then pulling it back, or first pulling back the whole elliptic 2 form to upstairs and then applying the Z residue is the same thing. Yeah, AZ is this log tangent bundle that I alluded to before. It's just vector fields which are tangent to Z. Okay, so this is not just at the level of Lie algebroids. It's in fact true at the level of Poisson manifolds. And there you use a result of Polishchuk, which basically describes when does a blow up of a thing admit a Poisson structure, if the bottom one does. And you just get this sort of, it always allows a blow up. And it's in fact log Poisson now. So what you can do is take an elliptic Poisson manifold, blow up D, and you get a log Poisson manifold with boundary. If you do this in the case where lambda is equal to 0, so the elliptic residue is 0, and you assume that pi is proper, as we could arrange before, then the log Poisson structure will also be proper. And for that, we need that, first of all, we need to know what properness means for log Poisson things, but it's similar to before. It's that it's one form that you get via applying the residue map also gives you this vibration. So it has compact leaves again. And yeah, that's true because of this intertwining of the residues. So you can blow up, and then properness will be preserved in the lambda equals 0 case. Okay, so now let's move on. Oh, first, maybe give you the summary. I was smart enough to first give a summary. So we start at the bottom here. We have X and pi. Pi is elliptic. We noticed that we could create this Lie algebroid, which is either A, D, or this more fancy notation. This notation is also, of course, very much related to what's going on in algebraic geometry. And there we noted that we could lift it there and find it to be dual to an elliptic symplectic object. So this is the bivector I'm writing in this sort of weird notation here. The blow-up procedure is via this map P, which first of all does this. So it allows for a Poisson map over here. But also we know that because this thing is log Poisson, it in turn can be lifted to its log tangent bundle. And this is a nice diagram that commutes. So now you see some Lie algebroids appearing. And then, of course, it's easy to ask yourself, OK, now what would be the groupoids that are supposed to go along with this? OK.
Ralph, can I ask you something? Can you explain the relationship between the symplectic foliations in the singular locus in these blow-ups and the one downstairs in the elliptic?
Yeah. So if you have a log Poisson manifold, right, it's always co-rank 1 on Z. So there are again 2 cases, right? The lambda is equal to 0 or lambda is not equal to 0. In the lambda equals to 0 case, then that's also why I was caring about this properness here. You see, in fact, that one of the one forms that you were using to cut out the symplectic foliation downstairs for the elliptic guy, that's alpha 1, that's the radial residue guy, is in fact the one that's cutting out the symplectic foliation upstairs. So that is, I guess, the description. These maps here, like Z over S1 and D over T2, they're also a commutative square. In the lambda non-equal 0 case, the Poisson structure on D is given by a non-degenerate one. And the one on Z is still corank 1 because it's just like products of that.
But do you get like Poisson maps between the divisors upstairs and downstairs, or the restriction? What is going on?
Yeah, I guess so. I guess there's a Poisson map from the restricted Poisson structure on Z to downstairs. Yeah.
Okay. Thanks.
Yeah.
Ralph, let me ask you about this slide on the left side. This symplectic form that you build, omega and omega tilde, how do they relate via phi?
So this map, so if you pull back omega via phi, you get omega tilde. So it's like it's like a symplectic map.
Okay.
And then you might wonder like, oh, the one is a Poisson, it's also symplectic. Yeah, this map phi is a fiberwise isomorphism.
Great, I see. And just another question, I may be a bit lost with some details, but this symplectic form, I mean, a Poisson manifold is the same as somehow a symplectic Lie algeroid, no? In the sense that it's a Lie algeroid together with a symplectic form on the total space of the Lie algeroid, no, that is compatible with the algeroid structure, etc. But this symplectic form is not on the total that you are mentioning here. It's not the one in the space, no?
No, that's right. So this is like how you should think of these Lie algebroids. They're constructed in exactly the manner that is needed to desingularize the Poisson structure. So the Lie algebroids on the left side, they are basically isomorphic to the tangent bundle where pi and pi tilde live, except where they should be different, namely on Z or on D respectively. And then it's really, this is a symplectic Lie algebroid, yes, but it's not in the sort of more higher version that you're describing. It's really a down-to-earth one. This is a Lie algebroid. It has a two form which is closed and non-degenerate. Hence, it has a Poisson bivector which is closed and non-degenerate. And the anchor map is a Poisson map between Lie algebroids with such structures, namely this guy and the tangent bundle that you're used to. Yeah.
Okay.
Yeah. Okay, so this is the picture we have now. There's some Lie algebroids around, there's some elliptic and log symplectic forms. And now we would like to do some groupoid stuff. One thing to note, by the way, as I will be describing shortly, is that the thing that I want to do, namely construct the groupoids for the ones downstairs, has been solved for the ones upstairs by Gautieri and Lee. So let's move on. So first I need to tell a little bit about what symplectic groupoids are and how to do this stuff in the log case. That will take me a bit of time. So let's go into it. So I'm assuming you know a little bit about groupoids. Yeah, if not, there are objects which you can denote like this. They're basically the global counterparts of Lie groups. If you think of Lie algebroids as being sort of a counterpart of a Lie algebra. And my structure maps are denoted like this. You can then put a geometric structure on the object, which needs to, of course, be compatible with the groupoid structure. That is one way to write it is by, it's just a Poisson bivector that is on the manifold G. And it being compatible with what's going on G, with this S and T and stuff, is one way to write it is saying that the graph of the multiplication is a coisotropic submanifold in this product of three guys. So graph of multiplication should be familiar to you, but it's basically saying like, oh, you take two things in there and then it should multiply to a third. So that's why it's in a product of three Gs. Okay. So for me, symplectic groupoids are really Poisson groupoids, where it so happens that pi G is non-degenerate. So I'm really using the bivector point of view here. If you have a groupoid, as you know, you can differentiate it. So you apply the Lie functor, Lie, and then you get a Lie algebroid again. And we say that this guy is then integrating Lie of G. But not all Lie algebroids are integrable. So if I'm saying like, oh, I want to construct the groupoids of an elliptic object, I first need to, of course, know that these exist or prove that they exist or something like that. Now, if you start with a Poisson manifold x comma pi, then there's always a Lie algebroid around, which is T star, and that this pi is just there to note that pi is the anchor map that you give it, and it also corresponds to the bracket. Now, if this thing is integrable, then we know that its largest integration, which is SSC, it's like source simply connected, will be symplectic. But not all of the integrations need to be symplectic. So if you take a general Lie algebroid, sorry, A, then the Weinstein groupoid is this largest one. And if there is a smallest one, it's called the adjoint groupoid. But this one is not necessarily existing, even if it is integrable. Why are they called largest and smallest? Yeah, there's some universal properties going on, but basically, if you have any integration, then it fits in a sequence of groupoid morphisms like this. It sort of is squeezed in between them. What I want to do today is construct the smallest ones that are there. So that is special, that these even exist for general Lie algebroids. And in order to know that that's even possible, we use some results of other authors, of course. First, De Boer showed that such an adjoint groupoid in general exists if the Lie algebroid you're using is almost injective, which is this condition we were talking about before. So it's injective on sections. All of the Lie algebroids that we've seen so far today are of this form. And André Dacre-Sambon took this a little bit further and brought a certain class of Poisson structures into the picture. Namely, they defined the Poisson structure to be almost regular. So it's not the same as being almost injective. If the module it defines, so pi sharp of gamma of t star x, is projective. So this is a singular foliation. You can put some complexly supported stuff here if you want, but it doesn't really matter. This is a singular foliation, and it can be projective or not. If it is, then the Poisson structure is said to be almost regular. Now, the word almost regular is not chosen randomly, of course, because being almost regular is saying that you are generically regular. So you must be almost everywhere regular, but it's more than that. And yeah, you can read their paper for specifics, of course. But as it turns out, this is precisely the condition you need to put such that the holonomy groupoid of the singular foliation f pi is smooth. And then there is thus then a smooth adjoint integration. And they also show that this thing is always Poisson then. So, okay, good. If we can manage to figure out that our Poisson structure is almost regular, then we know that there's a hope of finding the object that we want to construct. Well, they show a little bit more. Yeah?
Sorry, when you, in the previous slide, when you say that this is precisely the case where its holonomy groupoid is smooth.
Yeah.
What precisely do you mean by holonomy groupoid? Is a definition by Marco and Jacobos? Is this one?
Yeah, it's the André Dacre-Scandalis one. That one yeah. That one always exists for singular foliations, as they show, but it's not always smooth.
Yeah.
It's just like fiber-wise smooth, or some diffeology stuff or something like that. But when it's actually a Lie groupoid, that happens exactly when the module you're working with is projective. Yeah.
So this is the definition that you're using, the one.
Yeah, yeah.
The word. Okay,
thanks. Okay, moving on. So we know that our Poisson
structures. Sorry, Ralph.
Yeah.
Just a couple of comments, because this definition that you are making of almost regular makes sense for any algebroid, right?
Of course, yeah.
So, and also the De Boer case is a special case of the almost regular case, right?
Yeah, yeah, that's right.
Okay.
There is a little bit of a specialness that's going on for the algebroids which are defined by a Poisson manner, namely pi is skew, and that, well, André Dacre-Sambon explained this neatly to you, means that the being almost regular in the Poisson case, for example, only depends on the decomposition into leaves. That's something that you cannot expect to happen in general for a Lie algebroid. So there's some specialness that's going on in the Poisson case, but indeed, like most of the definitions also make sense in general. Okay, yeah, moving on. So one thing you note, just straight from the get-go, is that if you are generically non-degenerate, then you are certainly generically regular, right? And you're in fact also almost regular. So log Poisson guys and elliptic Poisson guys, they're almost regular. And hence by the result, we know already, of course, that they have adjoint integrations. We know, in fact, that the adjoint groupoid for T star is symplectic in that case. So we cannot just expect a Poisson groupoid as adjoint integration, but in fact, it will be symplectic. And then because the smallest integration is symplectic, all other integrations will also be. Okay. Yes. So what we will do is try to integrate T star, right? But instead, we will integrate this funny letter over here, R pi. R pi is the object you get by just applying Serre-Swan to the module. So F pi is projective because it's almost regular. So you get a Lie algebroid, R pi. And this thing is, in the general case, not isomorphic to T star, but because it's generically non-degenerate, it will be. So T star is just isomorphic to R pi. And then you might wonder, like, why are you doing this? Well, the reason why this is useful is because here we have made the module F pi explicitly a submodule of the module of vector fields. This is a singular foliation, right? So it sits inside gamma tx. And what we have done in a way is traded the complicatedness of the bundle with the complicatedness of the anchor map. Here, the bundle is very simple, you might think, like it's just T star, right? And all the information is contained in, well, the anchor and the bracket, pi. While over here, the bundle is more complicated, as we will see, even though they're isomorphic. But the anchor map is just the inclusion, or the map induced by the inclusions on sections. So it's more easy. Anyways, if you do this, you get sequences like this for the elliptic and log cases. We have our Tx over here, the elliptic tangent bundle. And then as it turns out, this R pi guy fits in here. So it sort of gives you a Lie algebroid sequence here. And the same is true in the log case. And then what we, of course, want to do is integrate Tx, integrate this guy, and then hopefully also integrate this guy. And the same for the log. OK. So let's first now recall how to construct some groupoids in the log Poisson case. And for that, I'll need two specific groupoids, both of which are, well, it's not entirely true, but both of which will be adjoint integrations. The first of which is, of course, very simple, right? It's just a pair groupoid. This one has, as its Lie algebroid, the tangent bundle. And it's, in fact, an adjoint integration that possibly needs, in fact, that X is connected, because otherwise you need to throw away like some of the components. But let's assume X is connected. The slightly more complicated one is called the relative pair groupoid, where you start with a fibration from your manifold X onto something else, and then you essentially take the fiber product along the map. So you take something which sits inside the pair groupoid. It's just all points which have the same image under F. Yeah, this thing is also not adjoint integration unless you take away again these components if you need to do that. The Lie algebroid of this guy is the kernel of TF. Okay, so now I'm describing work by Galtieri and Lee. You start with a manifold X and a hypersurface Z. And then this Lie algebroid pair is just a Lie algebroid A over X and a Lie subalgebroid B over Z. What you can then do is modify the Lie algebroid A via this manner. So you say that you're only looking at sections of A, which when you restrict lie in B. Now, as it turns out, because Z is a hypersurface, this gives you a projective module. Hence, there will be something called A dot dot B, which has that as its sheaf of sections, and this will again be a Lie algebroid. So if you do this procedure, you modify A over B. And as I'm writing here below, there will be an induced Lie algebroid morphism from this modification to the original guy. There's also a sort of analog of this the other way around, but I think it would be a little bit too annoying for you to hear out what this is. Essentially, what this is a Lie subalgebroid, right? So there's an injective morphism. What you need for this copair, is instead of an injective morphism, you need a surjective comorphism. I don't really want to explain to you what a comorphism of Lie algebroids is, but if you're familiar with it, then there you go. You can modify it in a similar manner. And it satisfies these types of relations if you dualize. Of course, if you dualize a Lie algebroid, what do you get, right? You get some object. Sure, you can give it names, you can study it. But this is certainly true at the level of vector bundles, that these are isomorphisms. If there's more structure, then it will be more true, but this is certainly true at the level of vector bundles. Okay, so why do you want to do this? Well, Galtieri and Lee show you that this is a very useful procedure. And yeah, this is another nasty slide. I hope you can at least get the gist of it. They notice that you can modify Lie algebroids, yes. And now if you have an integration of everything, so you have an integration of A and B, then there's a way to find an integration of the modification. And that should be done in this way. You can blow up the groupoid G along H and take away certain certain strata that you need to remove. And if you do that, you get another groupoid. That one will have, as its Lie algebroid, the modification you want. And then this theorem that I'm quoting here is saying that this can also be done in the Poisson context. So if you have a Poisson groupoid and a Poisson subgroupoid, which is closed, and the Lie bialgebroids, so not algebroids, but bialgebroids are given by A and A star, B and B star, then if it can be blown up, that is this condition that I'm writing here, then it can be blown up in a Poisson manner, and you in fact get everything you want. So this procedure is saying that if you know how to construct the correct Lie algebroid, so if you know that it is a modification of A by something, and you can integrate these parts, A and B have integrations G and H, then this theorem tells you that, okay, now you just chuck it in there, and then it constructs for you the groupoid you need. Yeah, there are some C's going around here, like C. That is because we want adjoint integrations, and for being adjoint, you need to not have any useless data. So you need to take the largest S-connected widely subgroupoid by taking connect components of identity. So you need to throw away stuff that is just there for stupid reasons. You already saw this in the pair groupoid case. Like if you have a manifold which consists of two connected components, the pair groupoid should just be product of one component, product of the other component, not all possible products. So you're doing something like this here in order to retain adjointness. Okay, so they have this result, and now they applied it to the log case, and it gives you this. So this will take us another few minutes to digest. So you take a log Poisson manifold, and I've already given it these tildes because for us it will be the blow up of something, right? So it needs to be proper, which then via applying the residue map to the log symplectic form gave us this vibration from Z onto S1. So the leaves of the induced Poisson structure on Z are compact, and they're in fact given by this sort of mapping torus thing. Then what they're saying is that you can find an integration of the log tangent bundle, T x tilde minus log Z, and it's this guy. So you know, of course, what the pair groupoid is. You know, of course, what the pair groupoid of Z is. You need to take the adjoint version of it. So if Z has multiple components, you need to throw away this useless data. You need to apply the previous result to get the blow-up groupoid of them. And then you need to, again, throw away possible some information. This is now an object, which is, via the result, a Poisson groupoid. And in fact, the Poisson structure that it carries is log. So it has a log Poisson structure. So the first bullet gives you this. If you have X with pi tilde, then the pair groupoid will certainly be will certainly be a Poisson groupoid which maps onto pi tilde. And then what they're telling you is that the first integration you want of the log tangent bundle is this thing over here, the log pair groupoid. The thing you might want based on the title of the talk is not some integration of the log tangent bundle, but a symplectic groupoid. And that's this second object on the left, or third object. That's in the second bullet point. It's called the log Poisson groupoid in my language. It is, again, given to us by the Guattari-Lie statement by doing this now. So instead of modifying the groupoid or the algebroid using the whole pair groupoid, you need to only take the relative pair groupoid with respect to the foliation that's present on Z. So the Lie algebroid you get is not that of the log tangent bundle, but this thing, which is the elementary modification of Tx tilde by the kernel of alpha. And that turns out to be T star. So you have, via this procedure, created an adjoint integration of T star, and it will in fact be symplectic. So out of the result, you get this. Okay, so I think I have one nice slide over here, which sort of summarizes what's going on. And maybe someone wants to ask something? Yes?
Yeah, let me ask you about these adjoint groupoids that you were telling us in the previous slide. Do you know if they are Hausdorff, or do you have any criteria to say when are they Hausdorff or not?
Yeah. So my memory escapes me a little bit, but this is certainly treated by Gualtieri Lee. Yes, I think these ones will be Hausdorff. I need to think again what's actually true, but this is known. Yeah. So in the log case, you get this. We already had this sequence of algebroids on the bottom, and now we get this sequence of groupoids at the top. Yeah?
I think I want to make a comment. There is work by the Board and Scandalis where they give a construction of blow-up, more general blow-up construction. So maybe it should be compared at some point with this work by Gualtieri and Lee.
Yeah. What was mentioned was work by De Boer and Scandalis on also blowing up groupoids.
Yeah.
Yes, I think this is certainly at least similar, but I believe it is slightly different the way in which they blow up. But for example, the base manifold is not changing when we do this blow by Gualtieri and Lee.
They take the tangent groupoid of Kohn and then they quotient by the action of R plus, more or less.
Yeah.
But anyway, just a suggestion. One might.
Yeah. Yeah, it's in fact something that I'll touch upon at the very end. Because I'm now going to describe how to use this for our case. We would like to not use this, but yeah, we have to now go through the log world. So we're getting also into the more work in progress territory. So my answers to your questions will be more and more vague, but let's move on. This is the log setting. Let's now try to figure out what to do in the elliptic setting. So that's the third thing. I have a little bit of time. So what we want is to start with elliptic Poisson manifold xd pi, blow it up, and then do this. So you might think that you can just directly construct the groupoids downstairs, so over x, but we don't know currently how to do that. So what we're going to do is go to the blow up, use the Gualtieri-Lee result, not exactly the theorem just now, but their constructions, and then obtain some groupoids over x tilde, and then hopefully get rid of this blow up procedure again by taking the quotient along P. And then you get groupoids over x. So this blow up thing that we've done, right? I've described how to do that. So now let's turn to the second and third one. And in fact, I'll talk now about the third thing. How would you quotient? Okay, so here's a little bit of general discussion. If you open up the book by Mackenzie on the Lie groupoids and Lie algebroids, then you find in some chapter the notion of a smooth congruence. So there's various ways to describe how to take quotients of Lie groupoids. I'm using this one because we need to take it over a varying base. So yeah, I'm not giving you the definition of a congruence, but it's a pair, S, R, which sits inside. You can think of this as the pair groupoid of G and the pair groupoid of X. And that is, of course, not too strange because if you take a quotient, what you need to do is identify certain things. So you need to quotient by an equivalence relation, which things should be the same. And an equivalence relation is the same thing as a subgroupoid of the pair groupoid. So a smooth congruence is sort of the groupoid version of that. You need to take this thing to be satisfying certain conditions, such as this is a subgroupoid of this, and there's some further compatibility, which I'm not spelling out. But then Mackenzie proves for you that this is true. So if you have such a smooth congruence, this is enough information to find a quotient. So there's a one-to-one correspondence between such a congruence and this. A Lie groupoid vibration from the original guy to the quotient, where you are quotienting possibly both G and X. Okay. Now, what you get then is a Lie groupoid vibration. In particular, the bottom map F will be a surjective submersion from X to X prime. Now, what we want to do is take a quotient of groupoids along P, the blowdown map. It is, however, not a surjective submersion. So we cannot use this smooth congruence business to get our quotient because it will just not happen. The congruence that we use is not going to be smooth. But our map P is, of course, not a crazy map, right? It's just a blowdown map. So if you restrict it to the complement of Z, it's just an isomorphism, doesn't do anything. So it's certainly a surjective submersion. But also the restricted map on Z is a surjective submersion. So now the idea that we have is to do this quotient procedure in the complement and on Z and hopefully combine it in some way. And I think I'm describing here how to do that. So what you can do is prove this result. So it's again a bit of a mouthful, but what this is describing is the following sort of simple idea. We want to take a quotient over a big manifold, X tilde. However, it will not be via smooth congruence. So we split it up into two parts. Here the part is Z and the complement of Z. These two parts need to be such that they are invariant under the groupoid. Of course, if one of them is, then the other one is as well. That's why I'm only writing this. And then you find smooth congruences on each of these parts. Well, you only really need to find it over Z because in the complement of Z, the map is not doing anything. So you also don't need to quotient anything. And then in order to glue it together in some way to get a congruence again, we need this notion of minimality. And that is not explained here, but it is basically saying that if you're taking the quotient of groupoids, you need to ensure that you're only taking the quotient of the base manifold. So the S fibers all remain isomorphic. That is also what you can expect to need to happen because, for example, as I was saying before, the log tangent bundle upstairs in the blowup is fiber-wise isomorphic to the elliptic tangent bundle downstairs. So there's, like in the fibers, there's not so much happening, just the manifold base. Well, this is the result you get. It's a theorem, I guess, but it's really tailor-made for what we're doing right now. It's basically saying that if you have the data to quotient over Z, and it's minimal in this precise sense, it basically means that there's some PBG groupoid, if that makes sense to you, that we're using here. Then you can glue it together, and then you get what you want. So then the quotient exists, it will be smooth, and it has a Lie groupoid morphism that's induced. So we need to know, for example, that the base manifold X that we obtain in this manner is a smooth manifold before we can do this. Like typically you cannot just take, oh, let me take the quotient of a manifold over here and over there, and then hope that the glued bit will still be smooth. That is something we need to put here. So this is not a very strong result if you want. It is really only applicable in very specific instances, which we have occurring here. Anyways,
right.
This is some result, yes?
I may be a bit confused here. Away from the singular locus,
yeah,
isn't the map one-to-one?
Yeah.
So do you need to do any reduction outside there?
No.
You are saying that two kind of reduction, no, on the singular locus and outside the singular locus. But I don't see why you need to reduce outside the singular locus.
You're not, that's what I'm saying. Like, because the map is just one-to-one, it's a local diffeomorphism, it's not doing anything. The congruence that you use there is just, it's doing nothing. It's quotienting nothing. However, it needs to glue together with the smooth congruence on Z to be a congruence. And then typically you cannot expect, if you just have a congruence, so it's not a Lie subgroupoid, it's just not Lie, that if you take the quotient of Lie objects via just congruences, that the result will again be Lie. So I'm doing nothing outside of Z, I'm doing something on Z, but I need to globally know that the thing I get then is smooth. And that is what this result is saying.
Okay, thanks.
Yeah. Okay. Yeah, maybe I can say a little bit more about how to now apply it. So let's move on. So the first thing we can, I think, prove is this thing. You take your elliptic Poisson manifold XD pi, you blow it up, you choose a co-orientation. As I was saying before, together with the elliptic ideal, that gives you a complex structure on the normal bundle to D, yeah? But it also gives you this principal U1 bundle structure on Z. And that is enough to be able to construct this minimal congruence. And then if you do it via the previous result, you get, by taking the pair groupoid upstairs, which is the object that is constructed to us by Galtieri and Lie, this thing, if you quotient it, it will be the adjoint integration of the elliptic tangent bundle. So let's see here. This sequence we know, right? Here we just have the pair groupoid. This is fine. This is the one constructed by Galtieri and Lie. And if you apply the quotient construction, you get the adjoint integration of the elliptic tangent bundle. Okay. Yes. The next thing you want to do is to show that this is also true at the level of Poisson groupoids. And for that, we need to have this congruent story that I was butchering a little bit just now at the level of Poisson groupoids. And that is something that is still work in progress, because quoting Poisson groupoids is a little bit more tricky. Okay, but you expect, of course, that here there's a log Poisson structure, that you would also be able to carry that through the quotient construction to not only get this thing as a groupoid, but as a Poisson groupoid. And then it will satisfy this stuff. So this is not yet symplectic anything, right? This is just the integration of the elliptic tangent bundle. What now to do with the integration of T star? Well, that relies again on this dichotomy. Sorry, here. It's either 0 or non-zero. And in the 0 case, as in the Gauthieron-Lie setting, we need to assume properness. So here is a line saying that we assume what we need. Then what I think I know how to prove is that this object will be the adjoint integration of T star. So it's again using this dot dot notation. That is the blow-up procedure by Gauthieron-Lie. And now you should not take the relative pair groupoid with respect to alpha, but with respect to both of them, like alpha 1 and alpha 2. And then there will be natural groupoid morphisms here. But here I'm claiming that they're Poisson. Yeah, that I don't know yet, because then again, I need to show that this is, well, okay. If this is the adjoint integration of T star, then it will be symplectic via the Anderson-Bohm result. But I want to know that it's symplectic via the quotient procedure. And that, again, is not done yet. Yeah, here you go. So you apply the Gauthieron-Lie stuff, and then you quotient, and then you get something. In
Ralph,
yeah.
Sorry, can I ask you one thing? Because you are assuming properness, you have this local model, right?
Yeah.
This semi-global local model around the
that doesn't need properness.
Right.
Yeah.
And don't you know how to integrate the local model?
No.
Because all these difficulties that you are having, if you can do this procedure by finding the adjoint integration of the local model, then you can check locally whether these statements are true.
Yeah. So I know. Yeah, I understand what you mean. This is also what I would like to be able to do, but I'm not able to construct the groupoid in this manner. So I need to sort of, if I know what's happening on, yeah, I understand what you mean. This is certainly something that possibly could be done, but the reason why we're doing this sort of roundabout way is that the only way in which we know how to modify groupoids to get the correct behavior is when it's done along codimension 1 substrata. So the blow-up procedure only works then. Otherwise, not yet known how to do it. But yeah, this is a nice picture that we hope to get. So not all of this is true yet, right? But you see all the Lie algebroids and all the groupoids here. And especially the fact that you are obtaining Poisson groupoids is not proven. One thing to note, for example, is that these ones up top, this one, this one, this one, are constructed by Gauthieron-Lie. So this one is symplectic. The one we are quotienting is further to the left of that one. So it will not be symplectic anymore. It will be a pre-symplectic groupoid. So we need to take a quotient of a pre-symplectic groupoid and then get a symplectic Poisson groupoid. Anyways, this is something that that still needs to be done. But yeah, I got a nice diagram for you. Just to finish up, because I think my time is also running out. I can be briefer here, but in the non-zero case, I haven't spent too much time figuring that out. But again, you of course expect a similar picture. You need to define some object, which I have some ideas, but for this talk I just put question marks. And then it will again be the adjoint integration. It will be Poisson, and you get a diagram like this, which is basically the same diagram as before, except the left side over here is swapped. So things that I want to, of course, do to figure out the end of the project is to actually construct this last thing, the question mark, to perform the quotient procedure that we have, not just for groupoids, but for ones with extra structure that we need. And the third thing that I'm writing here is more along the lines of what Rui is saying, I think, is that it should be possible that you use directly the elliptic ideal, so downstairs, to do your modification of the groupoid, instead of first blowing it up, making it log, then doing Gautier-Lie, and then quotienting, which is like going around like this, where you really just want to go directly. But that is something that we have not been able to achieve yet. Anyways, this is what I want to say, so thanks for your attention.